The universe is full of mysteries that we're still trying to understand. Beyond Earth, strange and incredible things are happening in space, things that challenge what we know about how the universe works. From unexplained signals to bizarre planets and stars, space is full of surprises. In this documentary, we'll look at some of the most unusual and puzzling mysteries in the universe. These are the questions that even scientists can't fully answer, showing us just how much there is left to discover. The universe is home to numerous black holes, some of which are among the most enigmatic and puzzling phenomena known to science. Black holes are typically detected by their interactions with surrounding matter. When a black hole pulls in nearby gas and dust, this material forms an accretion disk, heating up due to immense gravitational forces and emitting radiation detectable by telescopes. Other black holes reveal themselves through the gravitational waves they produce when merging with another compact object. However, a subset of black holes defies these detection methods entirely. These are known as silent or quiet black holes. Quiet black holes do not emit detectable radiation, nor do they actively accrete matter. They remain invisible to conventional observational tools like X-ray or radio telescopes, which are designed to detect energetic emissions from active black holes. The lack of activity makes their identification exceedingly difficult. These objects are hypothesized to exist in significant numbers throughout the universe, representing a potentially vast population of cosmic objects that remain hidden from even the most advanced instruments. The silence of these black holes poses significant challenges for astronomers. Active black holes, like those found at the centers of galaxies or in binary star systems, are relatively easier to identify because of their dramatic interactions with their environment. Quiet black holes, on the other hand, lack these distinguishing features. Without accreting matter or emitting radiation, they become effectively invisible against the backdrop of space. Detecting them requires indirect methods, such as observing their gravitational influence on nearby stars or gas clouds. For instance, a star orbiting an unseen, massive object with no visible companion could indicate the presence of a quiet black hole. Theoretical models suggest that these silent black holes may far outnumber their active counterparts. Stellar evolution predicts that many massive stars end their lives in supernovae, collapsing into black holes. However, not all black holes will find themselves in environments rich with matter to accrete. Many may form in regions of space where gas and dust are sparse, leaving them without material to consume. Others might have accreted matter in the past but exhausted their immediate surroundings, rendering them dormant. The implications of a vast population of undetected black holes are profound. If quiet black holes dominate in number, they could account for a significant portion of the missing mass in the universe. This missing mass is a persistent mystery in astrophysics, as observed gravitational effects in galaxies and galaxy clusters suggest there is far more mass present than can be accounted for by visible matter. While much of this is attributed to dark matter, silent black holes could contribute to the overall mass budget of the universe. Efforts to detect quiet black holes are ongoing and rely heavily on advancements in technology and observational techniques. Gravitational lensing offers one potential method. When a massive object, such as a black hole, passes in front of a distant light source, it bends the light from that source due to its gravitational field. This effect, known as microlensing, can reveal the presence of a compact, massive object, even if it emits no light. Large-scale surveys of the sky, which monitor millions of stars for microlensing events, could uncover hidden populations of black holes. Another avenue involves studying the motions of stars in the Milky Way. A star's velocity can be influenced by the gravitational pull of nearby objects. By analyzing these motions with extreme precision, astronomers can infer the presence of unseen massive companions, potentially identifying quiet black holes. Instruments like the Gaia spacecraft, which maps the positions and motions of billions of stars, are instrumental in this effort. Understanding the population of quiet black holes also has implications for black hole formation theories. Their existence suggests that black hole formation is not always accompanied by violent, observable phenomena. Some black holes may form through less energetic processes, or their environments may shield their formation from detection. This could expand our understanding of how massive stars evolve and collapse. Furthermore, the study of silent black holes contributes to our understanding of gravitational waves. Binary systems containing quiet black holes could merge, producing gravitational waves detectable by observatories like LIGO and Virgo. These events provide valuable data about the masses and spins of black holes, including those that might otherwise remain undetected. The phenomenon of time-distorted galaxies stands as one of the most perplexing enigmas in modern astrophysics. Observations reveal that certain galaxies appear to stretch or contract in time, exhibiting behaviors that deviate from the expected patterns of cosmic expansion. This temporal distortion creates a sense that these galaxies are either moving slower or faster than their counterparts in the universe, challenging our understanding of time and space on a cosmological scale. At the heart of this mystery lies the relativistic nature of time itself. According to Einstein's theory of general relativity, the flow of time is not uniform but is influenced by gravity and relative motion. Massive objects, such as galaxies, can create significant distortions in spacetime, resulting in time dilation. In the case of time-distorted galaxies, this effect could be occurring on an extraordinary scale, influenced by unseen gravitational forces or unique relativistic circumstances. One possible explanation is the presence of massive unseen gravitational fields, such as those generated by dark matter or black holes. Dark matter, an elusive substance that does not emit or absorb light, is known to account for much of the gravitational influence in the universe. If concentrated in certain regions, it could warp space-time enough to alter the perception of time for distant galaxies. Similarly, supermassive black holes, which are commonly found at the centers of galaxies, could create extreme gravitational fields that stretch or compress time in their vicinity. These effects may extend far beyond the immediate vicinity of the black hole, influencing entire galaxies. Another factor contributing to this phenomenon could be the relative velocity of these galaxies. The universe's expansion, described by the Hubble constant, means galaxies are moving away from each other. However, individual galaxies can also have additional velocities due to gravitational interactions. If a galaxy is moving toward us or away from us at exceptionally high speeds, its light will be subject to redshift or blueshift, phenomena where the wavelength of light changes due to motion. This relativistic Doppler effect can create the illusion of time distortion, as the observed processes within the galaxy, such as star formation or rotation, appear to slow down or speed up. In addition to relativistic motion, these distortions may be tied to the concept of cosmic expansion itself. The universe is not expanding uniformly, but is influenced by variations in dark energy, the mysterious force driving the acceleration of expansion. Some regions of space may experience different rates of expansion due to local variations in dark energy density. Galaxies located in such regions might appear time-stretched compared to others, further complicating the observational data. A less conventional hypothesis involves the possibility of interactions between parallel universes or higher dimensional phenomena. Theoretical physics suggests that our universe may be just one of many within a multiverse, and certain interactions at the boundaries of these universes could manifest as distortions in spacetime. While purely speculative, such ideas highlight the vastness of what remains unknown about the nature of time and space. Observational techniques used to study these galaxies include the analysis of their light curves, spectral lines, and gravitational lensing effects. Gravitational lensing, where the light from a distant galaxy is bent and magnified by the gravitational field of a massive object between the galaxy and Earth, provides a unique opportunity to study time distortions. When light from a galaxy passes near a massive object, such as a galaxy cluster, it can travel along multiple paths of varying lengths. This can result in multiple images of the same galaxy appearing at different points in time, effectively creating a natural time machine for astronomers. Further studies are needed to determine whether time-distorted galaxies are more common in certain regions of the universe or are random occurrences. Advances in telescope technology, such as the James Webb Space Telescope and future next-generation observatories, will allow scientists to observe these phenomena with unprecedented detail. By analyzing the light from these galaxies across a wide range of wavelengths, researchers hope to unravel the physical processes behind the time distortions. Understanding time-distorted galaxies is not just about deciphering an astronomical curiosity. It has profound implications for our understanding of the universe's fundamental laws. These galaxies provide natural laboratories for testing the limits of general relativity and exploring the interaction between gravity, motion, and the fabric of spacetime. They may also offer insights into the nature of dark matter and dark energy, two of the most elusive components of the cosmos. Alien star chemical signatures represent one of the most perplexing and fascinating mysteries in modern astrophysics. Certain stars exhibit unusual chemical compositions, unlike those typically observed in other stars of similar type. These anomalies challenge our understanding of stellar formation and evolution, leading to two primary explanations: unknown natural processes or the possibility of advanced extraterrestrial technology. Stars are composed primarily of hydrogen and helium, with trace amounts of heavier elements. This composition results from nuclear fusion processes in the stellar core, where lighter elements are converted into heavier ones over billions of years. However, some stars deviate from these expected patterns. They contain elements or isotopic ratios not easily explained by natural nucleosynthesis. Such anomalies suggest that their chemical composition might have been altered post-formation, possibly due to external contamination or rare astrophysical processes. One hypothesis points to natural enrichment mechanisms. Stars that form in regions of the galaxy influenced by previous supernovae might acquire unique chemical signatures. Supernovae, the explosive deaths of massive stars, eject vast amounts of heavy elements and exotic isotopes into the surrounding space. These remnants can mix with nearby gas clouds, potentially influencing the formation of new stars. However, in some cases, the detected anomalies go beyond what is expected from known supernova enrichment processes, leaving scientists searching for alternative explanations. Another possibility involves interactions with exotic particles or phenomena not yet fully understood. For instance, stars near the center of the galaxy, where conditions are extreme, might experience influences from high-energy cosmic rays or interactions with dark matter. These interactions could subtly alter their chemical makeup, producing signatures that seem unnatural when compared to other stars. While this explanation remains speculative, it highlights the need to explore the boundaries of known physics to account for such anomalies. The more speculative but equally intriguing explanation involves the possibility of artificial influence. Advanced civilizations, if they exist, might have the capability to manipulate stars for energy harvesting or other purposes. Concepts such as Dyson spheres, hypothetical megastructures built around stars to capture energy, have been proposed as potential markers of extraterrestrial intelligence. These structures, or similar constructs, could theoretically alter the chemical composition of a star, either intentionally or as a byproduct of their activities. For instance, a civilization might introduce specific elements or isotopes into a star's atmosphere to optimize energy extraction, leaving behind a detectable chemical fingerprint. Additionally, some scientists suggest that advanced civilizations might engage in large-scale astroengineering projects, including the deliberate alteration of stellar properties to extend a star's lifespan or to create a more favorable environment for surrounding planets. Such activities could produce chemical signatures that appear anomalous to observers on Earth. While there is currently no direct evidence to support this hypothesis, the idea remains a topic of serious scientific inquiry as it aligns with the principle of seeking technosignatures, observable signs of advanced technological activity in the universe. Another perspective involves the potential role of neutron stars, black holes, or other compact objects in influencing the chemical properties of nearby stars. These objects exert powerful gravitational and electromagnetic forces, which might trigger unusual reactions in a star's outer layers. However, the specific mechanisms required to produce the observed anomalies are not well understood, making this an area of ongoing investigation. In some cases, these chemical signatures are detected in stars located in relatively isolated regions, far from areas of active star formation or recent supernova activity. This isolation adds to the mystery, as it eliminates some of the more conventional explanations. Detailed spectroscopic analysis of these stars often reveals unexpected elements, such as technetium, a radioactive element not typically found in stars because of its short half-life, or unusually high levels of heavy metals like gold and platinum. Such findings raise the possibility of unique astrophysical events or interactions that have not yet been fully modeled. To study these anomalies, astronomers use advanced tools such as high-resolution spectrographs in space-based observatories. These instruments allow for precise measurements of a star's light spectrum, revealing its chemical composition with remarkable detail. Researchers compare these spectra to theoretical models and laboratory experiments to identify potential causes for the discrepancies. Dark matter halos, vast invisible structures surrounding galaxies, are critical to our understanding of the universe. These halos, believed to consist of dark matter, a form of matter that neither emits nor absorbs light, play a pivotal role in the formation and stability of galaxies. They are detected indirectly, primarily through their gravitational effects on visible matter such as stars, gas, and galaxies themselves. One of the most perplexing phenomena related to dark matter halos is their unexpected rotational behavior. Galaxies are observed to rotate in a way that cannot be explained by visible matter alone. Based on these observations, astrophysicists conclude that dark matter must surround galaxies in a roughly spherical distribution, forming what is referred to as a halo. However, measurements of these halos' rotational speeds reveal a mystery that challenges current models of dark matter. Contrary to predictions, the rotation of dark matter halos often appears to be faster than anticipated. This anomaly is particularly intriguing because under standard cosmological theories, dark matter is classified as non-interacting. This means it should not interact with itself or other matter except through gravity. Yet the unexpectedly rapid rotation suggests that some additional interaction or process might be at work. Standard dark matter models are based on the concept of cold dark matter, CDM, which assumes that dark matter particles move slowly and do not collide or interact with one another. This theory has been remarkably successful in explaining large-scale cosmic structures, such as galaxy clusters and the cosmic web. However, the faster-than-predicted rotation speeds of dark matter halos appear to contradict these models. Observations imply that dark matter may not be entirely cold or non-interacting. Instead, it might exhibit some degree of interaction, either with itself or with other forces and particles. These interactions could alter its behavior, including its distribution and motion. The implications of this anomaly are profound. If dark matter interacts with itself, this could lead to new insights into its fundamental nature. For instance, self-interacting dark matter could explain certain features observed in the structure of galaxies. Simulations based on non-interacting dark matter predict that dark matter halos should have a highly dense core, but many observed galaxies instead exhibit a core distribution, where the density of dark matter is more evenly spread. Self-interactions could account for this discrepancy by redistributing dark matter within the halo. Furthermore, if dark matter exhibits self-interactions, it may also influence the angular momentum of the halo. This could explain the unexpected rotational speeds. In essence, these interactions might transfer energy and momentum within the dark matter halo, causing it to rotate faster than initially predicted. Such a mechanism would challenge the traditional view of dark matter as a passive background force and suggest a much more dynamic role in the evolution of galaxies. Another possible explanation involves the presence of dark forces. Just as ordinary matter interacts through forces like electromagnetism and the weak nuclear force, dark matter might interact through a dark sector of forces unknown to current physics. These forces could act only on dark matter, creating effects such as faster rotation or altered distribution patterns. This possibility has inspired theoretical work suggesting that dark matter could consist of multiple types of particles, each interacting through forces specific to the dark sector. The study of rotating dark matter halos also raises questions about the relationship between dark matter and visible matter. Observations show that the distribution of dark matter within a halo is often closely linked to the distribution of stars and gas in the galaxy it surrounds. This phenomenon, known as the galaxy halo connection, suggests that some interaction or feedback mechanism ties the behavior of dark matter to the visible components of galaxies. Faster than expected halo rotation might provide clues about how these processes work, potentially linking dark matter's properties to the formation and evolution of galaxies. Efforts to resolve the mystery of rotating dark matter halos rely on a combination of observations, simulations, and theoretical models. Observationally, astronomers use techniques like gravitational lensing, galaxy rotation curves, and measurements of the cosmic microwave background to probe the properties of dark matter halos. These methods allow researchers to infer the distribution and motion of dark matter, even though it is invisible. Advances in telescope technology and the development of new observational techniques continue to refine these measurements, providing more detailed data on the behavior of dark matter. Fluctuating cosmic filaments, vast structures spanning millions of light years, are among the most remarkable discoveries in modern astronomy. These colossal filaments form part of the cosmic web, a massive network connecting galaxies, galaxy clusters, and intergalactic matter. Recent observations suggest these filaments exhibit a phenomenon likened to breathing, expanding and contracting over time. This unexpected dynamic behavior challenges current understandings of large-scale cosmic structures and hints at deeper unseen forces governing the universe. The cosmic web is primarily composed of dark matter, with a smaller fraction of baryonic or normal matter interwoven within it. Galaxies and galaxy clusters reside at the intersections of these filaments, which act as conduits for matter and energy across the universe. Scientists previously regarded these filaments as static structures, defined by the gravitational pull of dark matter and the mass of the galaxies within them. However, detailed deep-field surveys and simulations have revealed subtle but measurable oscillations in the length, width, and density of these filaments. This fluctuation resembles a rhythmic expansion and contraction. It is a subtle motion, occurring over vast timescales, potentially billions of years. These shifts are far beyond the scale of direct human perception, but are evident through meticulous comparisons of data collected across different epochs of the universe's history. The discovery emerged from precise measurements of galaxy velocities and their positions along filaments. Galaxies appear to migrate along these filaments in complex patterns that correlate with the observed filamentary shifts. One possible explanation for this phenomenon lies in the interplay between gravitational forces and dark energy. Dark energy, the mysterious force driving the accelerated expansion of the universe, may influence the dynamics of these filaments. As galaxies pull on each other through gravity, dark energy could create a counterforce, causing the filaments to oscillate rather than remain in a fixed state. This interaction might explain why the filaments are not static, but exhibit this almost pulsating behavior. Another theory connects the phenomenon to the distribution of mass within the cosmic web. Fluctuations in the density of dark matter, combined with baryonic matter's interaction with surrounding intergalactic gas, could induce a wave-like movement. Simulations suggest that regions with higher mass concentrations exert greater gravitational influence, causing adjacent filamentary regions to compress or stretch over time. These interactions might trigger cascading effects, resulting in the large-scale rhythmic patterns observed in these structures. Magnetic fields could also play a role in this process. While magnetic fields are generally weak on cosmic scales, their cumulative influence over millions of light years could contribute to shaping the movement within filaments. Magnetic fields may interact with charged particles in the filaments, inducing slight oscillatory behaviors that propagate through the network. These fluctuations might also affect the flow of matter and energy through the filaments. As intergalactic gas and galaxies move along these structures, the oscillatory behavior could modulate the rate at which material is funneled into galaxy clusters. This could influence galaxy formation rates, star formation activity, and even the overall distribution of galaxies in the universe. In this sense, the filaments may act as dynamic highways, constantly adjusting the flow of matter across the cosmos. The study of fluctuating cosmic filaments also provides insights into the universe's past and future. By analyzing these motions, scientists can refine models of how structures formed following the Big Bang. This information enhances our understanding of the mechanisms that shape the large-scale structure of the cosmos over billions of years. It also helps to predict how the universe might evolve under the continued influence of dark energy. Additionally, this discovery underscores the complexity of the cosmic web. It suggests that even the most massive and seemingly immutable structures are subject to change. This dynamic view of the universe challenges the conventional perspective of static structures governed solely by gravity. Instead, it reveals a more intricate interplay of forces shaping the cosmos. The discovery of fluctuating cosmic filaments raises questions about the underlying laws of the universe. What mechanisms drive this oscillation? How do dark matter, dark energy, and other forces interact to produce such behavior on such massive scales? Answering these questions will require more advanced simulations and deeper observations using next-generation telescopes capable of mapping the cosmic web in unprecedented detail. The vanishing galaxy problem represents one of the most perplexing mysteries in astrophysics. Over the decades, astronomers have cataloged countless galaxies in the universe, using advanced telescopes and surveys to map the cosmos in incredible detail. Yet in some cases, galaxies that were once observed and documented appear to no longer exist. This phenomenon challenges fundamental understanding of galactic evolution and the forces governing the universe. Galaxies are vast collections of stars, gas, dust, and dark matter bound together by gravity. They are not static. Their dynamics are influenced by various factors, including gravitational interactions, mergers, and cosmic expansion. Despite this dynamic nature, the disappearance of entire galaxies from observable records suggests processes that are poorly understood and potentially transformative for modern astrophysics. One possible explanation is that these galaxies may have merged with larger structures. Galactic mergers are a common phenomenon in the universe, driven by gravitational attraction. When two galaxies interact, their stars, gas, and dark matter halos combine, forming a single, more massive galaxy. During the merger, the individual identities of the galaxies are erased, creating structures that may no longer resemble the original entities. Observationally, this could explain why a galaxy might vanish from a catalog. It could now exist as part of a larger and more complex system. Alternatively, some of these galaxies might have undergone processes that rendered them invisible to current detection methods. For example, a galaxy could lose much of its luminous material, such as stars and gas, over time. Stars within galaxies undergo life cycles, and when enough stars reach the end of their lifespans, the galaxy could become less visible in certain wavelengths. Additionally, interactions with other galaxies or intergalactic forces could strip away gas and dust, effectively extinguishing the galaxy's ability to form new stars. This process, known as quenching, could lead to a dark, inert galaxy that is nearly impossible to detect without highly sensitive instruments. Another possibility involves extreme gravitational phenomena. A galaxy's mass, particularly its dark matter halo, could collapse into a central point, forming a supermassive black hole. If enough material falls into such a black hole, it could disrupt the galactic structure to the point that it no longer resembles a traditional galaxy. While the black hole itself would emit high-energy radiation during active phases, the galaxy as a whole might fade from detection in standard surveys. Dark matter also plays a significant role in this mystery. Most galaxies are believed to be surrounded by vast halos of dark matter, an invisible substance that constitutes most of the universe's mass. If a galaxy's luminous material were stripped away, the remaining dark matter halo would be nearly impossible to observe directly. Such a dark galaxy might still exist, but without stars or gas, it would evade detection by current optical or radio telescopes. Cosmic expansion, particularly the accelerating expansion of the universe driven by dark energy, could also contribute to the vanishing galaxy problem. Galaxies that were once visible might now be receding beyond the observable horizon due to the universe's continued expansion. As they move farther away, their light is redshifted to longer wavelengths, eventually becoming undetectable by instruments designed to observe specific parts of the electromagnetic spectrum. Over cosmic timescales, this redshifting effect could cause galaxies to disappear from observational reach, even if they still exist. Instrumental and observational biases also warrant consideration. Early galaxy surveys were conducted with less sensitive technology, which may have resulted in misclassifications or overestimations of galaxy counts. Some vanished galaxies might never have existed as separate entities, but were instead misinterpreted due to the limitations of early data. Improved technology and methods in modern astrophysics allow astronomers to revisit old observations and refine their conclusions, but discrepancies remain. This mystery also raises questions about the role of galaxy clusters in intergalactic environments. Galaxies within dense clusters are subject to significant gravitational and tidal forces, which can strip them of material or disrupt their structures. In some cases, a galaxy within a cluster might be absorbed into the cluster's diffuse light, effectively hiding it from traditional observations. Similarly, interactions with intergalactic phenomena, such as high-energy radiation or magnetic fields, might influence a galaxy's detectability. Supernovae are among the most powerful and dramatic events in the universe. These stellar explosions occur when a massive star exhausts its nuclear fuel and collapses under its own gravity, or when a white dwarf in a binary system accretes enough material to ignite runaway nuclear fusion. For decades, astrophysicists have studied supernovae to understand their causes, dynamics, and effects on the cosmos. However, some supernovae do not conform to the established theoretical models. These anomalies, known as the wrong types of supernovae, challenge conventional astrophysical theories. Supernovae are categorized into two main types: Type 1 and Type 2. Type Ryran supernovae occur in systems where a white dwarf accretes matter from a companion star, while Type 2 supernovae arise from the collapse of massive stars with hydrogen-rich outer layers. Within these classifications, theoretical models predict specific ranges of energy output, light curves, and spectra based on known physical processes. Yet some observed supernovae deviate significantly from these expectations. These outliers exhibit energy outputs that are either much higher or much lower than the theoretical limits, suggesting gaps in our understanding of stellar deaths. One example of such anomalies is the superluminous supernovae, SLSNE. These are explosions that release up to 100 times more energy than a typical supernova. Their brightness is so extreme that they can outshine entire galaxies for weeks or months. Traditional models struggle to explain how such enormous amounts of energy can be produced. Some hypotheses suggest that these supernovae may involve a magnetar, a rapidly spinning neutron star with an exceptionally strong magnetic field. As the magnetar spins down, it releases vast amounts of energy, potentially driving the intense luminosity of SLSN. Other theories propose interactions between the supernova ejecta and dense shells of material expelled by the star before its explosion. The collision of these layers could convert kinetic energy into light, amplifying the brightness beyond normal limits. On the opposite end of the spectrum are underluminous supernovae, which release far less energy than expected. These faint supernovae challenge our understanding of stellar collapse. One possibility is that these explosions result from failed supernovae, where the collapse of a massive star does not produce the usual energetic outburst. Instead, much of the star's mass may fall directly into a black hole, leaving behind only a weak or partial explosion. Alternatively, these events might involve unusual progenitor stars with unique compositions or structures that suppress the energy of the explosion. Another intriguing category of anomalous supernovae involves those with atypical light curves or chemical signatures. For instance, some supernovae exhibit unusually slow declines in brightness, which could indicate prolonged energy input from an unknown mechanism. Others display unexpected abundances of heavy elements, suggesting that the nuclear reactions during the explosion may differ from standard predictions. These discrepancies raise questions about the conditions and processes leading up to these events. One particularly puzzling phenomenon is the existence of calcium-rich transients, a type of supernova that produces disproportionately large amounts of calcium compared to other elements. These explosions are less luminous and occur in environments where typical supernovae are not expected, such as the outskirts of galaxies or even intergalactic space. Their origins remain unclear, but one hypothesis involves the merger of two compact objects, such as white dwarfs, which could generate the observed chemical signatures without producing the energy of a standard supernova. Dark matter may also play a role in some of these anomalous supernovae. Dark matter, which constitutes a significant portion of the universe's mass but does not emit or absorb light, interacts with ordinary matter primarily through gravity. Some researchers speculate that interactions between dark matter and stars could influence the dynamics of stellar collapse or explosion. For example, if dark matter particles accumulate in the core of a star, they could affect the core's stability and trigger unusual types of explosions. Alternatively, dark matter interactions might suppress the energy of a supernova, leading to the observed under-luminous events. Another theory involves binary star systems. Many stars exist in binary systems, where two stars orbit each other. The interactions between the stars, such as mass transfer or gravitational influences, can significantly alter the evolution of one or both stars. These interactions might lead to unique conditions that result in non-standard supernovae. For instance, if a massive star loses its outer layers to a companion star before collapsing, the explosion could exhibit atypical light curves or chemical signatures. Hyper-rapid planetary migration refers to the phenomenon in which certain exoplanets appear to have shifted their orbits far faster than what current models of planetary dynamics can explain. In traditional astrophysical models, planetary migration is a gradual process driven by interactions between a planet and the protoplanetary disk, gravitational encounters with other bodies, or tidal forces over millions of years. However, observations of some exoplanet systems have revealed orbital shifts that are orders of magnitude faster than anticipated. This phenomenon challenges existing theories and introduces a new layer of complexity to our understanding of planetary formation and evolution. One of the primary explanations for hyper-rapid migration involves gravitational interactions within young planetary systems. In the early stages of a planetary system's life, the protoplanetary disk, a dense mixture of gas and dust surrounding a young star, can create dynamic and chaotic conditions. In such environments, planets can exchange angular momentum with the disk material, leading to significant orbital shifts. While this mechanism is well known and studied, the rapid timescales observed in certain systems suggest that either the density of the disk or the mass of the interacting bodies may be far greater than previously assumed. Another possible explanation centers around interactions with massive unseen companions. These companions could be either large planets, failed stars such as brown dwarfs, or even stellar mass objects within the system. If such a body exerts a strong gravitational influence on a nearby planet, it could cause rapid changes in the planet's orbital path. These interactions might include close encounters or resonances, where the gravitational pull of the massive companion synchronizes with the orbit of the migrating planet, amplifying its motion over a relatively short time. Hyper-rapid planetary migration may also be facilitated by the chaotic dynamics of multi-planet systems. When several planets are in close proximity, their mutual gravitational interactions can destabilize their orbits. This can lead to a scenario known as planet-planet scattering, where one or more planets are flung into new orbits. In extreme cases, these scattering events can push a planet much closer to or farther from its host star in a matter of thousands or even hundreds of years, a blink of an eye in cosmic terms. Such events might also eject planets entirely from the system, creating rogue planets drifting through interstellar space. Young planetary systems in particular are prone to hyper-rapid migration because of their inherent instability. During the first few million years after a star forms, the gravitational environment around it is turbulent. Planets in these systems are not yet fully settled into stable orbits, making them more susceptible to rapid shifts. Observations of young stars have revealed protoplanets with eccentric and highly elliptical orbits, indicating that significant migration may have occurred shortly after their formation. A significant factor in this phenomenon could involve the mass and composition of the protoplanetary disk itself. In some cases, disks with higher than average masses or densities could exert much stronger torques on planets, accelerating their migration rates. Additionally, the interaction between the magnetic fields of the host star and the disk could introduce forces that further alter planetary orbits on short timescales. Certain types of exoplanets, such as hot Jupiters, are often cited as examples of rapid migration. These gas giants are found in extremely close orbits around their host stars, far closer than where they are believed to have formed. Traditional models suggest that these planets originated in the cooler, outer regions of their systems and migrated inward over millions of years. However, the discovery of some hot Jupiters in very young systems raises the possibility that their migration occurred on a much shorter timeline, potentially through hyper-rapid processes. The phenomenon of hyper-rapid migration also has implications for the detection and study of exoplanets. Many current detection methods, such as the transit and radial velocity techniques, rely on relatively stable orbits to identify planets and characterize their properties. If planets are undergoing rapid migration, their changing orbits could complicate detection efforts or lead to misinterpretations of observational data. For instance, a planet in the midst of hyper-rapid migration might appear to have an unusually short orbital period or exhibit erratic changes in its transit timing, making it difficult to pin down its true characteristics. Cosmic string shadows are one of the most intriguing and potentially groundbreaking concepts in modern cosmology. These faint distortions, observed in the cosmic microwave background, CMB radiation, may represent the subtle imprints of ancient cosmic strings. These theoretical structures, if confirmed, could revolutionize our understanding of the universe's formation and the fundamental forces governing spacetime. Cosmic strings are hypothesized one-dimensional defects in spacetime, remnants of symmetry-breaking processes that occurred during the universe's earliest moments. Shortly after the Big Bang, as the universe cooled and transitioned through various states, fundamental forces that were once unified began to separate. This process, similar to the way cracks form in ice as water freezes, could have created cosmic strings as stable, thread-like structures stretching across the cosmos. Unlike ordinary matter, cosmic strings are purely theoretical constructs, predicted by certain models of high-energy physics, including those involving grand unified theories, GUTS, and string theory. The idea of cosmic string shadows arises from their potential impact on the CMB. The CMB is the faint afterglow of the Big Bang, a nearly uniform background of radiation that fills the universe. It is remarkably smooth, but contains tiny fluctuations, which reflect variations in the density of matter in the early universe. These fluctuations later influence the formation of galaxies and large-scale structures. If cosmic strings exist, they could leave unique imprints on the CMB, detectable as faint, linear distortions or discontinuities in this radiation. The mechanism behind these distortions lies in the extreme properties of cosmic strings. These structures are believed to be incredibly dense and possess immense gravitational effects despite their narrow, one-dimensional form. A single cosmic string could warp spacetime significantly, creating what is known as a conical geometry. This effect means that light passing near a cosmic string would be deflected in a specific, predictable way. As the CMB radiation travels through the universe and encounters a cosmic string, this deflection could create faint, linear features in the observed radiation patterns. These are referred to as cosmic string shadows. Detecting cosmic string shadows is an extraordinary challenge due to their subtle nature. The CMB is already faint, and the distortions caused by cosmic strings would be even fainter, buried within the noise of other astrophysical phenomena. However, advances in observational techniques and instruments, such as high-resolution satellite missions like the Planck spacecraft and future observatories, have made it possible to study the CMB with unprecedented detail. Researchers are meticulously analyzing this data to identify patterns consistent with the predicted signatures of cosmic strings. If confirmed, cosmic strings could provide invaluable insights into the universe's infancy and the conditions that prevailed during the first fractions of a second after the Big Bang. Their existence would lend support to specific theories about symmetry breaking and phase transitions in the early universe. Furthermore, studying these structures could enhance our understanding of fundamental physics, potentially offering clues about the unification of forces, the nature of dark matter, and the dynamics of spacetime. Theoretical models suggest that cosmic strings could also interact with one another. When two strings collide or intersect, they may form loops or reconnect, releasing energy in the form of gravitational waves. These gravitational waves, ripples in space-time, are another potential avenue for detecting the presence of cosmic strings. Modern gravitational wave observatories like LIGO and Virgo are actively searching for signals that could be attributed to such interactions. Despite their theoretical appeal, cosmic strings remain hypothetical. Alternative explanations for the observed CMB distortions, such as instrumental noise or other astrophysical phenomena, must be rigorously ruled out before cosmic strings can be confirmed. Nonetheless, the search for cosmic string shadows continues to be a high-priority effort in the field of cosmology, driven by their profound implications for our understanding of the universe. The study of cosmic string shadows exemplifies the intersection of theoretical physics and observational astronomy. It requires sophisticated mathematical models to predict the properties of these structures and cutting-edge technology to detect their faint imprints. The pursuit of cosmic strings not only probes the origins of the universe, but also pushes the boundaries of human knowledge, challenging scientists to refine their theories and develop innovative methods to explore the cosmos. Galaxy clusters, some of the largest structures in the universe, typically exhibit massive halos of hot gas. These halos are detectable through X-ray emissions, generated as the gas heats up to millions of degrees due to gravitational compression and the interaction of galaxies within the cluster. The presence of this hot gas is not just common, it is expected under the standard models of cluster formation. However, certain galaxy clusters lack these hot gas halos, a phenomenon that presents a puzzling anomaly for astronomers and challenges long-standing assumptions about the behavior and evolution of such massive structures. Galaxy clusters form through the gradual accumulation of smaller structures, such as groups of galaxies and dark matter halos. During this process, gravitational energy is converted into heat, producing the characteristic hot gas. This gas fills the space between the galaxies within the cluster and forms an intracluster medium, ICM, a fundamental component of cluster environments. The absence of this gas, therefore, contradicts predictions made by established astrophysical models. One of the main implications of this absence is the need to reconsider the processes involved in the formation and evolution of galaxy clusters. Standard theories suggest that the energy released during the cluster's formation should prevent gas from cooling rapidly. This energy balance is maintained by shocks and turbulence created as galaxies merge within the cluster, keeping the gas hot and preventing it from condensing into denser forms. When hot gas is missing, it suggests that either the energy input is insufficient or there is an unknown mechanism facilitating rapid cooling or removal of the gas. The missing hot gas might indicate processes that dissipate or expel it from the cluster. One possible explanation involves the role of active galactic nuclei, AGN. These supermassive black holes, located at the centers of many galaxies, can release powerful jets and outflows of energy. If AGN activity is unusually high in a particular cluster, it might expel the hot gas before it can settle into the expected halo. Alternatively, the gas might cool so rapidly that it transitions into forms not detectable by X-ray telescopes, such as dense molecular clouds or diffuse cooler plasma. Another hypothesis relates to the role of dark matter. Dark matter, the unseen mass that dominates the gravitational potential of galaxy clusters, is essential for holding hot gas within the cluster. If the dark matter distribution in a cluster is less concentrated or unusually shaped, it might fail to retain the hot gas. This scenario would not only explain the absence of gas, but also point to unique or irregular dark matter structures in these clusters. Interactions with the surrounding cosmic environment might also play a role. Galaxy clusters are not isolated entities but exist within the cosmic web, surrounded by vast filaments of gas and galaxies. Some clusters may be located in regions with lower than average gas density, leading to insufficient material to form the expected hot halos. Alternatively, the surrounding environment might strip away the gas through processes such as ram pressure stripping, where the motion of the cluster through the intergalactic medium removes its gas content. These clusters also raise questions about the thermal history of their intracluster medium. If hot gas was present in the past but is now absent, it suggests a dynamic and evolving system rather than a static one. Understanding the timeline of these changes could provide insights into the broader processes shaping galaxy clusters and their environments over billions of years. Furthermore, missing hot gas affects more than just the clusters themselves. It also has implications for the broader study of the universe's large-scale structure. Galaxy clusters are used as cosmological probes to understand the distribution of matter, the behavior of dark energy, and the history of the universe's expansion. If certain clusters lack hot gas, it introduces biases into these studies, potentially leading to errors in estimates of cosmic parameters. Observations of galaxy clusters without hot gas challenge astronomers to develop new techniques and theories. Current observational tools, such as X-ray telescopes, are designed to detect hot, luminous gas. The absence of such emissions does not necessarily mean the gas is entirely missing. It could simply be in a state that is difficult to observe with existing technology. Future instruments capable of detecting cooler or more diffuse forms of gas may provide critical insights into these enigmatic systems. Asteroids, the rocky remnants from the formation of our solar system, have long been objects of fascination for scientists and astronomers. Typically, they follow predictable orbits within our solar system, often residing in stable regions like the asteroid belt between Mars and Jupiter. However, a small, extraordinary category of these objects defies conventional expectations. Known as hypervelocity asteroids, these space rocks travel through the cosmos at speeds far exceeding those of typical solar system objects. These speeds often surpass several 100,000 kilometers per hour, and their behavior offers intriguing insights into the violent and dynamic nature of the universe. The origin of these extreme rogue asteroids is one of the most captivating mysteries in astrophysics. Unlike asteroids that are native to our solar system, hypervelocity asteroids are believed to have been ejected from other star systems. This interstellar origin suggests that these objects were launched into space by dramatic and energetic processes. Scientists propose that such events include gravitational slingshots during close encounters with massive celestial bodies, such as stars, black holes, or neutron stars. In some cases, these asteroids may have been expelled from their original systems during the explosive death throes of stars, such as supernovae. The immense force generated by these cosmic events can propel solid fragments into interstellar space at astonishing speeds. Another potential mechanism involves interactions within binary star systems. In these systems, two stars orbit a common center of mass, often accompanied by planets, moons, and asteroid belts. If one star in such a system undergoes a supernova or a dramatic collapse, the remaining star and any surrounding material may be thrown into chaotic motion. In this scenario, asteroids that were once in stable orbits around the stars could be hurled out of the system entirely. This expulsion can accelerate them to hypervelocity, allowing them to traverse vast distances across the galaxy. Hypervelocity asteroids are distinct not only in their speed, but also in their trajectories. Unlike most solar system objects, which follow elliptical orbits around the Sun, these interstellar visitors often exhibit hyperbolic trajectories. A hyperbolic trajectory indicates that the object is not gravitationally bound to the Sun and will eventually leave the solar system entirely. This is in stark contrast to the closed, looping paths of native asteroids. Observing these unique trajectories is a key method by which astronomers identify potential interstellar objects. Studying hypervelocity asteroids provides an invaluable opportunity to explore the processes that govern the evolution of planetary systems. These objects act as messengers from other star systems, carrying with them information about the materials, conditions, and forces present in their regions of origin. Analyzing their composition can reveal clues about the chemical makeup of distant systems and help scientists understand how planetary systems form and evolve throughout the galaxy. However, detecting and studying these objects poses significant challenges. Their high velocities and unpredictable paths make them difficult to observe for extended periods. Many hypervelocity asteroids pass through the solar system quickly, often escaping detection entirely. Advances in telescope technology and sky survey programs are essential for identifying and tracking these elusive objects. Instruments capable of rapidly scanning large portions of the sky and detecting fast-moving objects are particularly critical in this effort. The discovery of hypervelocity asteroids also raises important questions about their potential impact on Earth. Although their interstellar origin and high speeds make such events exceedingly rare, the possibility of a hypervelocity asteroid collision cannot be entirely dismissed. The energy released in such an impact would far exceed that of a collision with a typical asteroid, given the increased kinetic energy resulting from their immense speed. Understanding their trajectories and monitoring their presence is vital for planetary defense strategies. Beyond their scientific significance, hypervelocity asteroids challenge our understanding of the universe and our place within it. They highlight the interconnected nature of the cosmos, where events in distant star systems can have far-reaching consequences, even influencing our solar neighborhood. Each hypervelocity asteroid that enters the solar system represents a fragment of a larger story, one that involves the formation, destruction, and dynamic reshaping of star systems across billions of years. The universe, vast and ancient, holds many mysteries, but few are as puzzling as the strange alignments observed in the rotational axes of galaxies across enormous scales of space. Over billions of light years, these alignments challenge our understanding of cosmology and the forces shaping the universe. Known as the cosmic axis of rotation, this phenomenon involves galaxies aligning their spins in ways that defy expectations based on the random distribution of matter and energy in the universe. Galaxies rotate due to angular momentum inherited from the conditions of the early universe. According to standard cosmological models, these rotations should be distributed randomly when viewed across vast cosmic distances. However, observations suggest otherwise. Studies using data from large-scale galaxy surveys, such as the Sloan Digital Sky Survey, SDSS, and others, reveal an unexpected coherence in the spin orientations of galaxies. When viewed over regions spanning hundreds of millions or even billions of light years, galaxies appear to align their axes preferentially in certain directions. This large-scale alignment is particularly evident when studying the cosmic filaments, long, thread-like structures of galaxies and dark matter that make up the universe's vast web-like structure. These filaments are the scaffolding upon which the cosmos is built, and galaxies within them tend to exhibit spin axes that align parallel or perpendicular to the filaments. Such behavior indicates an underlying pattern that may be influenced by forces or mechanisms not yet fully understood. One hypothesis for this alignment involves the influence of dark matter. Dark matter, an invisible form of matter accounting for about 27% of the universe's total mass energy content, plays a crucial role in the formation and evolution of cosmic structures. Its gravitational effects shape the motion of galaxies and the formation of cosmic filaments. It is possible that dark matter halos, which envelop galaxies, exert subtle gravitational forces that influence the orientation of galaxies as they form and evolve within these filaments. If dark matter itself has intrinsic properties or interactions beyond what current theories predict, it could offer clues to why these alignments occur. Another possibility is that these alignments are remnants of the conditions in the early universe. The initial distribution of matter and energy after the Big Bang, influenced by quantum fluctuations and the rapid inflationary expansion of space, may have imprinted specific patterns that persist to this day. The rotational alignments could reflect these primordial conditions, serving as a cosmic fossil record of the universe's earliest moments. If true, studying these alignments could provide valuable insights into the physics of the early universe and the nature of cosmic inflation. Cosmic magnetic fields also present a potential explanation. Large-scale magnetic fields, though faint and poorly understood, permeate the universe and could influence the spin orientations of galaxies. These fields may interact with electrically charged particles within galaxies, subtly steering their rotational axes over time. If such magnetic fields were stronger or more coherent in the past, they could have left a detectable imprint on the alignment of galaxy spins. The discovery of these alignments has sparked debates among cosmologists and astrophysicists. Standard models of cosmology, which rely on the assumption of isotropy and homogeneity, that the universe looks the same in all directions, are challenged by evidence of such large-scale coherence. If these alignments are confirmed to be widespread and significant, they could imply the presence of unknown forces or interactions shaping the cosmos on a grand scale. To probe this mystery further, researchers are employing advanced telescopes and computational simulations. Observations of galaxy clusters, their spin orientations, and their positions within cosmic filaments are being analyzed in unprecedented detail. At the same time, simulations of cosmic evolution are being refined to incorporate potential factors, such as dark matter interactions, primordial conditions, and magnetic fields, to determine if they can reproduce the observed patterns. Despite the progress, many questions remain. Are these alignments a universal feature of the cosmos, or are they localized phenomena specific to certain regions or epochs of the universe's history? Could they point to entirely new physics beyond our current understanding? These mysteries underscore the importance of continuing to map the universe and develop theories capable of explaining its vast complexity. In the vast expanse of the universe, certain regions defy the predictable patterns of star distribution. One such area, nicknamed the Cosmic Chimney, is an enigmatic stretch of space located above the Milky Way's plane. Unlike most regions of the galaxy, which are densely populated with stars, this area appears unnervingly empty, as if a massive void has swept through, leaving behind a strikingly barren patch. The Cosmic Chimney has perplexed astronomers since its discovery. Its defining characteristic is the almost complete absence of stars in what should be an otherwise active stellar region. In astrophysical terms, this region exhibits an unusually low stellar density, suggesting the influence of an extraordinary phenomenon. Theories surrounding this anomaly seek to explain how such a void could form in a universe governed by well-understood principles of matter distribution. One leading hypothesis proposes that this void is the result of an ancient galactic wind. Galactic winds are powerful outflows of gas and particles generated by intense star formation, or the explosive deaths of stars such as supernovae. In the case of the Milky Way, early in its history, bursts of star-forming activity might have unleashed colossal streams of energy and matter. These winds could have swept through sections of the galaxy, pushing away gas and dust, the raw materials needed for star formation. Over millions of years, this process would have created a void-like structure, leaving a region like the Cosmic Chimney largely devoid of stars. Another intriguing explanation involves the role of dark energy or dark matter in shaping the structure of this region. Dark energy, which is thought to drive the accelerated expansion of the universe, could have played a part in disrupting the gravitational forces that typically cluster stars together. If dark energy interacted with the galactic material in an unusual way, it might have contributed to the dispersal of matter, preventing the formation of stars in this specific area. Similarly, the distribution of dark matter, an invisible form of matter that exerts gravitational influence, could provide clues. Dark matter acts as a framework for galaxies, anchoring stars and gas within its gravitational pull. A peculiar arrangement or deficiency of dark matter in this region might have resulted in the observed stellar void. Further complicating the mystery is the possibility that the Cosmic Chimney is not entirely devoid of matter, but instead contains diffuse gas or faint stars that are difficult to detect with current instruments. Some astronomers hypothesize that the region could harbor high-energy particles or radiation, remnants of the same galactic winds that originally shaped it. This would explain why traditional optical telescopes fail to capture any significant features within the chimney. Observations using other wavelengths, such as radio or X-rays, might eventually reveal hidden structures or phenomena within the void. The geometry of the Cosmic Chimney is also a subject of investigation. It appears to align vertically above the galactic plane, resembling a narrow column or tube extending outward from the Milky Way. This unusual shape suggests that the forces creating the void acted in a highly directional manner. The alignment might correlate with the orientation of magnetic fields in the galaxy, which can influence the flow of gas and charged particles. If the chimney is indeed shaped by magnetic forces, it could offer valuable insights into the large-scale magnetic structures of the Milky Way and their impact on galactic evolution. The study of such anomalies is not merely an exercise in curiosity, but also a window into understanding the broader processes governing galaxy formation and evolution. Regions like the Cosmic Chimney challenge existing models of star formation and distribution, prompting astronomers to refine their theories and develop new observational techniques. Future missions equipped with more advanced telescopes and instruments will be critical in unraveling the mystery of this peculiar void. One potential avenue for further research involves the mapping of similar voids in other galaxies. If structures resembling the cosmic chimney are found elsewhere, they could represent a common feature of galactic evolution, shaped by universal processes such as winds, magnetic fields, or dark energy. Alternatively, if the chimney proves to be unique to the Milky Way, it could point to a distinctive event or condition in our galaxy's history that created this anomaly. In the vast expanses of the universe, far removed from the dense regions of galaxies, astronomers have uncovered a phenomenon that challenges long-standing assumptions about star formation. Isolated pockets of space producing stars independently of any galaxy. These regions, informally referred to as intergalactic star factories, present an extraordinary puzzle and suggest the existence of processes or conditions not yet fully understood. Traditionally, stars are known to form within galaxies, gravitationally bound collections of gas, dust, stars, and dark matter. In these environments, gas clouds collapse under gravity, initiating nuclear fusion and giving birth to stars. Galaxies provide the dense, supportive environments necessary for this process, with gravitational forces, metallic elements, and shock waves from prior star deaths contributing to star formation. The discovery of rogue star factories, however, indicates that star formation is not strictly confined to galaxies, and that there may be untapped potential within the intergalactic medium. The intergalactic medium, IGM, the tenuous matter that exists between galaxies, was long thought to lack the density needed for star formation. However, observations from advanced telescopes, such as the Hubble Space Telescope and ALMA, Atacama Large Millimeter, Submillimeter Array, have detected bright, isolated regions of ultraviolet light, indicative of newly formed young stars, far from any nearby galaxy. This raises important questions. How can such regions sustain the necessary conditions for star formation? What mechanisms are driving the process without the infrastructure provided by a galaxy? One possibility is that these star factories are remnants of galactic collisions or interactions. When galaxies collide or pass close to one another, tidal forces can eject streams of gas into intergalactic space. Under specific conditions, these gas streams could clump together, becoming dense enough to trigger star formation. Another theory posits that these factories are fueled by primordial gas clouds left over from the early universe. These clouds, composed mostly of hydrogen and helium, might still contain regions dense enough to form stars under the right conditions. Another hypothesis involves the role of dark matter, the unseen substance that makes up about 27% of the universe. Dark matter's gravitational influence may be helping these gas pockets coalesce, providing the necessary compression for star formation in regions otherwise lacking significant gravitational forces. This would suggest that dark matter is not only a passive participant in cosmic structure, but an active player in facilitating astrophysical phenomena. Intergalactic star factories also challenge assumptions about metallicity in star formation. Metals, elements heavier than hydrogen and helium, are typically thought to be crucial for cooling gas clouds, enabling them to collapse into stars. However, the intergalactic medium is known for its low metallicity. If stars are forming in these environments, it implies that under certain conditions, stars can form with minimal metal content, echoing processes thought to have occurred in the early universe during the formation of the first stars. The discovery of these star factories is not just an academic curiosity. It has profound implications for our understanding of cosmic evolution. These regions could represent a previously unrecognized mode of star formation, one that operates outside the bounds of galaxies and contributes to the distribution of stars across the universe. Moreover, the study of intergalactic stars could offer insights into the behavior of baryonic matter and dark matter in intergalactic space. Further investigation into these rogue star-forming regions is essential. Future observations with next-generation telescopes like the James Webb Space Telescope and upcoming radio observatories will likely shed more light on the dynamics and composition of these star factories. Understanding these isolated phenomena could reveal missing pieces in the puzzle of how matter behaves on the largest cosmic scales. In conclusion, intergalactic star factories are a fascinating anomaly that challenges the conventional boundaries of astrophysics. They suggest that the universe harbors mechanisms of creation yet to be fully understood, pushing the frontiers of knowledge about where and how stars can form. These findings open a new chapter in the study of the cosmos, underscoring the extraordinary complexity and adaptability of the universe's processes. Gravitational wave detectors like LIGO and Virgo have revolutionized our understanding of the universe by capturing the ripples in space-time caused by cosmic events such as the merging of neutron stars or black holes. However, among the many detections, scientists have observed a puzzling phenomenon: bursts of gravitational waves that appear without any corresponding electromagnetic signals. These events, often referred to as invisible neutron-star collisions, have raised intriguing questions about their origins and the nature of the environments in which they occur. Neutron stars are the dense remnants of massive stars that have undergone supernova explosions. When two neutron stars collide, the immense energy of the event typically produces a burst of light or other electromagnetic emissions, such as gamma-ray bursts or visible afterglows. These emissions provide vital information about the nature of the collision and the matter involved. However, in some cases, gravitational wave detections are completely dark, with no detectable light or radiation accompanying the event. One explanation for these dark collisions is the possibility that they occur in environments where electromagnetic signals are entirely absorbed or blocked. For instance, the collision could take place within dense regions of gas and dust, which act as a shroud, preventing any light from escaping. Alternatively, the surrounding matter could include exotic materials that alter or suppress the expected emissions. Another possibility involves the nature of the objects involved in the collision. If one or both of the merging objects are black holes rather than neutron stars, the lack of light could be due to the absence of material capable of producing electromagnetic signals. Black holes are known for their extreme gravitational pull, which prevents even light from escaping. If a neutron star collides with a black hole, the black hole might swallow the neutron star and its material too quickly to produce detectable emissions. A particularly intriguing hypothesis involves the presence of exotic matter around the neutron stars. Neutron stars themselves are composed of highly compressed nuclear material, but under certain conditions, their outer layers might include unknown forms of matter. If these collisions occur in environments rich in such exotic materials, the mechanisms that typically produce light could be fundamentally altered, leading to faint or completely absent electromagnetic signals. These invisible events have significant implications for astrophysics. They challenge our understanding of neutron star and black hole environments and raise questions about how gravitational wave signals can be interpreted when traditional observation methods fail. Scientists are now exploring ways to refine gravitational wave analysis to extract more information from these mysterious events, potentially identifying clues hidden within the patterns of the waves themselves. The study of invisible neutron star collisions underscores the importance of multi-messenger astronomy, where gravitational waves, electromagnetic signals, and other forms of data work together to provide a complete picture of cosmic phenomena. As detection technology improves, researchers hope to uncover the missing pieces of these enigmatic events and shed light on the processes that render them invisible to traditional telescopes. In essence, the study of these invisible collisions offers a glimpse into some of the universe's most extreme and hidden processes, pushing the boundaries of our understanding of the cosmos. One of the most puzzling mysteries in cosmology today revolves around a phenomenon observed in distant supernova: the apparent deviation from expected time dilation effects. Time dilation, a fundamental consequence of Einstein's theory of relativity, predicts that as the universe expands, light traveling vast cosmic distances should appear stretched, and events such as supernova explosions should appear to occur more slowly when observed from Earth. However, certain distant supernovae challenge this expectation, suggesting an anomaly in the behavior of space-time on a universal scale. In a universe governed by the Standard Model of cosmology, time dilation correlates directly with the redshift of distant objects. Redshift is the lengthening of the wavelength of light as it travels through an expanding universe, making distant objects appear redder and their clocks appear to tick more slowly. For instance, a supernova at a high redshift should exhibit a clear, predictable slowdown in its light curve, how its brightness changes over time. Yet in some cases, the light curves of these distant supernova do not slow down as much as they theoretically should. This discrepancy has left scientists grappling with potential explanations. One possibility is that our understanding of space-time, particularly on cosmic scales, is incomplete. The very fabric of the universe might operate under dynamics that deviate from the assumptions embedded in Einstein's framework or the current cosmological model. Such deviations could suggest that space-time itself might be influenced by unknown forces or properties, potentially tied to quantum effects, dark energy, or other undiscovered phenomena. Another intriguing possibility involves hidden dynamics in the expansion rate of the universe. The standard model assumes a relatively uniform expansion, influenced primarily by dark energy, a mysterious force driving the acceleration of the universe. If, however, the expansion of the universe has been more erratic or influenced by additional, yet undetected forces, this could explain the anomaly. For example, certain regions of the universe might experience variations in the strength or effects of dark energy, leading to inconsistencies in time dilation across different observational points. It is also worth considering that the anomaly might point to limitations in our observational techniques or models. For instance, assumptions made about the intrinsic properties of these supernovae, such as their light emission profiles, might need revision. If distant supernovae evolve differently due to their unique environments, such as higher levels of cosmic radiation or variations in local matter density, their light curves might naturally deviate from predictions. This phenomenon has profound implications for our understanding of the cosmos. If the observed deviations in time dilation are indeed indicative of new physics, they could lead to a paradigm shift in how we view the universe. It might require reconciling general relativity with quantum mechanics on cosmic scales, revealing a deeper unified theory of space-time. Alternatively, it could provide new insights into the nature of dark energy, potentially unlocking answers about why the universe's expansion is accelerating. The challenge now lies in gathering more precise data and refining models to either confirm the anomaly or integrate it into existing frameworks. Future missions involving advanced telescopes and more comprehensive surveys of supernovae across a wide range of redshifts will be critical. As these efforts unfold, the mystery of cosmic time dilation anomalies will remain a focal point of inquiry, holding the potential to reshape our understanding of the universe itself. Planets orbiting white dwarfs, also known as ghost planets, are among the most astonishing discoveries in modern astronomy. White dwarfs are the remnants of stars that have exhausted their nuclear fuel, collapsing into dense, Earth-sized objects. They represent the final evolutionary stage for the vast majority of stars, including our own sun in the distant future. What makes the detection of planets around these stellar embers remarkable is the extreme conditions under which these planets exist. When a star reaches the end of its life, it undergoes a series of violent changes. For stars like our sun, this process involves expanding into a red giant, shedding its outer layers, and finally collapsing into a white dwarf. During this transformation, the intense heat and energy released by the star's death throes often obliterate any nearby planets. The closer planets are engulfed by the star's expansion or torn apart by tidal forces. This destructive process was long thought to leave no planets intact within the vicinity of the white dwarf. Yet astronomers have identified planets not only surviving, but orbiting within these once devastated systems. Some of these planets, located surprisingly close to the white dwarf, have led scientists to reconsider long-held assumptions about planetary resilience. The mechanisms by which these ghost planets persist are still under investigation, but several hypotheses provide plausible explanations. One possibility is that these planets were originally located at a safe distance during the star's death, avoiding the worst of the destruction. As the stellar system evolves, gravitational interactions, or the collapse of the star, may cause the planets to migrate inward, settling into close orbits around the white dwarf. This inward migration could occur over millions of years as the system stabilizes after the chaotic events of the star's collapse. Another explanation suggests that these planets formed or were captured after the star became a white dwarf. In systems where debris from the star's outer layers remains, there could be enough material for new planets to coalesce. Additionally, rogue planets, planets not bound to any particular star, may wander into the gravitational influence of the white dwarf, becoming trapped in orbit. The discovery of ghost planets has also been aided by advanced observational techniques. Using methods such as the transit method, where a planet passing in front of a star causes a detectable dip in its light, or gravitational microlensing, astronomers have been able to confirm the presence of these planets in unlikely locations. These techniques have revealed not only the existence of such planets, but also details about their size, composition, and orbital characteristics. Ghost planets challenge conventional ideas about planetary systems and their longevity. They demonstrate that planets are more resilient than previously believed, capable of surviving or adapting to the violent upheavals of their host stars' transformations. Their discovery has profound implications for the study of planetary systems, including our own. As we learn more about these planets, they offer insights into the future of Earth and in its neighboring planets when the Sun eventually becomes a white dwarf. In addition to reshaping theories of planetary resilience, ghost planets provide a unique environment for studying planetary evolution under extreme conditions. The intense radiation from the white dwarf, coupled with the gravitational stresses in such a system, creates a setting vastly different from that of planets orbiting stable stars like the Sun. Understanding how these planets interact with their host white dwarfs offers valuable information about the boundaries of planetary habitability and the mechanisms that govern planetary survival in the universe. In essence, ghost planets orbiting white dwarfs remind us that the universe is full of unexpected phenomena, challenging our assumptions and expanding our understanding of how celestial systems evolve and endure. The mystery of sub-Neptune planets is one of the most puzzling phenomena in the study of exoplanets. These planets, which are smaller than Neptune but significantly larger than Earth, are remarkably common across the galaxy. Observations from telescopes such as Kepler and TESS have revealed that sub-Neptune-sized exoplanets dominate the known exoplanet population. Despite their prevalence, our solar system lacks a single example of this type of planet. This absence raises significant questions about the processes that shaped our solar system and its divergence from the planetary systems observed elsewhere in the galaxy. Sub-Neptune planets typically range in size from about 1.5 to 4 times the radius of Earth. They are generally thought to have thick atmospheres composed of hydrogen and helium, with rocky or icy cores. Their sizes and compositions place them between terrestrial planets like Earth and Venus, and the gas giants such as Neptune and Uranus. This intermediate classification makes them a distinct category of planetary formation, yet the mechanisms responsible for their development are not fully understood. The absence of sub-Neptune planets in our solar system suggests that specific factors during its early formation may have played a critical role in shaping its unique planetary architecture. One hypothesis involves the early migration of Jupiter and Saturn. These gas giants are believed to have undergone significant movement during the early stages of the solar system's development. Models of planetary formation suggest that their migrations may have disrupted the protoplanetary disk, influencing the size and distribution of the material available for planet formation. Jupiter in particular may have acted as a gravitational barrier, preventing the accumulation of sufficient gas and dust in certain regions of the solar system. This disruption could have stunted the growth of potential sub-Neptune planets or led to their ejection from the system entirely. The gravitational influence of Saturn, combined with that of Jupiter, may have further contributed to clearing the region, leaving behind only the smaller terrestrial planets like Earth and the much larger gas and ice giants like Neptune and Uranus. Another factor could be the timing and efficiency of the disk's dissipation. Sub-Neptune planets are thought to form in regions where protoplanetary disks remain dense and gas-rich for extended periods. If the solar nebula, the cloud of gas and dust from which the solar system formed, dispersed relatively quickly, there may not have been enough time for sub-Neptune planets to coalesce. This rapid dissipation would favor the formation of smaller, rocky planets close to the Sun and larger gas giants in the outer regions. The phenomenon known as photoevaporation could also play a role. High-energy radiation from a young star can strip away the atmospheres of nearby planets, particularly those with lower gravity. In the solar system, the proximity of forming planets to the Sun and the intensity of early solar radiation may have removed the thick atmospheres needed to classify planets as sub-Neptunes. This would leave behind rocky planets with thinner atmospheres, like Earth, Venus, and Mars. Studying the prevalence of sub-Neptune planets in other star systems provides valuable insights into these missing planets. Exoplanet surveys indicate that such planets often occupy orbits close to their stars, in regions referred to as hot or warm zones. This contrasts sharply with the configuration of our solar system, where no such planets exist, and the closest planets to the Sun are small, rocky bodies. These differences highlight the complexity and variability of planetary formation processes across the galaxy. The mystery of sub-Neptune planets not only challenges our understanding of planetary formation, but also emphasizes the uniqueness of our solar system. Solving this puzzle requires further investigation of both exoplanet systems and the early dynamics of our own solar system. By combining advanced observational techniques with detailed theoretical models, scientists aim to uncover why our solar system is missing this ubiquitous class of planets and what that absence reveals about the processes that shaped our cosmic neighborhood. Black holes are among the most enigmatic objects in the universe, and their influence extends far beyond the boundaries of their event horizons. One of the most fascinating phenomena associated with black holes is their ability to generate sound waves. These sound waves are not like those experienced in Earth's atmosphere, but instead are created in the surrounding gas of the black hole. They are an intricate product of the immense gravitational forces exerted by the black hole on its environment. The pitch of these sound waves is extraordinarily low, far below the range of human hearing. For comparison, the frequency of these waves can be measured in cycles as long as several million years. These ultra-low frequencies fall in what scientists call the infrabass range, a realm entirely beyond the perception of human ears. Observations from instruments like NASA's Chandra X-ray Observatory have revealed these waves in the gas surrounding supermassive black holes, such as the one at the center of the Perseus galaxy cluster. The waves ripple outward in a manner akin to sound waves traveling through a medium, though on a cosmic scale. These sound waves are not random or inconsequential. They provide valuable insights into the nature of black holes and their environments. By analyzing these waves, scientists can extract critical information about the black hole's spin, its growth history, and its interactions with nearby matter. The spin of a black hole, for example, affects how it draws in matter from its accretion disk and influences the formation of jets that can extend across vast regions of space. The sound waves carry subtle details that reflect these processes, acting as a kind of fingerprint unique to each black hole. Moreover, the behavior of these sound waves helps astrophysicists understand how black holes influence their host galaxies. Black holes can regulate the temperature and movement of the surrounding gas, a process known as feedback. This feedback determines how galaxies evolve, affecting star formation and the distribution of matter within the galaxy. The sound waves produced by black holes are a crucial aspect of this feedback mechanism, redistributing energy within the galactic environment and preventing runaway cooling in massive gas clouds. The detection and study of these waves rely on advanced observational techniques. X-ray telescopes capable of capturing the hot gas surrounding black holes allow researchers to identify the ripples and map their propagation. By converting the wave frequencies into a format humans can interpret, scientists have even made it possible to listen to these cosmic sounds, providing a tangible connection to phenomena otherwise far removed from our sensory experience. In essence, black hole sound waves are a bridge between the incomprehensibly vast scale of the universe and the tangible methods by which we study it. They offer a unique perspective on the fundamental mechanics of black holes and their profound impact on the cosmic structures that surround them. Their study continues to unravel the mysteries of these celestial giants, revealing the intricate and dynamic processes that shape the universe. In the vast expanse of the universe, galaxies are expected to move randomly under the influence of local gravitational forces, following the well-studied principles of cosmic expansion and gravitational interaction. Yet astronomers have identified a puzzling anomaly. Clusters of galaxies, separated by millions of light years, appear to be moving in a synchronized manner. These motions are not random, but instead suggest a coherent flow that defies conventional understanding. This phenomenon has been termed galactic dark currents, and it represents one of the most intriguing mysteries in astrophysics. Galactic dark currents describe a large-scale movement of galaxies that align in the same direction, irrespective of their distance from one another. This phenomenon cannot be attributed to local gravitational effects or the influence of known cosmic structures, such as galaxy clusters or superclusters. Normally, galaxy motions are influenced by the gravitational pull of nearby masses, such as other galaxies or dark matter concentrations. However, in the case of these synchronized flows, the source of the influence is not apparent. The discovery of galactic dark currents began with observations of the so-called dark flow, a similar phenomenon where galaxy clusters appeared to be moving in the same direction, seemingly unaffected by the general expansion of the universe. Using advanced telescopes and instruments such as the Wilkinson Microwave Anisotropy Probe, WMAP, and later the Planck spacecraft, scientists observed deviations in the cosmic microwave background radiation that indicated these anomalous movements. These flows appeared to stretch beyond the observable universe, raising questions about the structures or forces that might lie beyond our observational limits. Galactic dark currents suggest the presence of forces or structures that we cannot directly observe. One hypothesis posits that these motions are caused by the gravitational pull of massive structures beyond the observable universe. According to this idea, our universe might be part of a much larger multiverse or embedded in a cosmic web of structures that extend beyond what we can see. These unseen structures, sometimes referred to as great attractors, could exert a gravitational influence on galaxies within our observable universe, causing this synchronized motion. Another possibility involves the nature of dark matter and dark energy. Dark matter, which constitutes roughly 27% of the universe's mass energy content, is invisible to conventional detection methods, but exerts gravitational effects on visible matter. Similarly, dark energy, which is thought to drive the accelerating expansion of the universe, could interact in ways not yet fully understood. It is possible that these mysterious components of the universe are interacting on scales far larger than previously imagined, creating the conditions for galactic dark currents. Additionally, some theories propose that the synchronization of galaxy movements could result from the influence of primordial gravitational waves or quantum fluctuations from the early universe. These fluctuations, originating shortly after the Big Bang, might have created a pattern of mass distribution that persists on cosmic scales, subtly directing the motion of galaxies even billions of years later. The scale of these synchronized motions challenges our understanding of the universe's structure. Observations suggest that galactic dark currents occur over distances far exceeding the size of known cosmic structures, such as superclusters and voids. For context, the largest known structure in the universe, the Hercules Corona Borealis Great Wall, spans about 10 billion light-years. Yet these synchronized motions appear to operate on even larger scales. This raises questions about the true extent of the universe and whether our observable universe is merely a small part of a much larger whole. The study of galactic dark currents has implications for several fundamental areas of cosmology. For one, it challenges the assumption that the universe is isotropic and homogeneous on the largest scales, a foundational principle of the Standard Model of cosmology. If galaxies are moving in coherent flows due to structures or forces beyond our observational reach, it suggests that the universe is more complex than current models can explain. Moreover, understanding galactic dark currents could provide insights into the nature of dark matter and dark energy, which remain among the greatest mysteries in modern science. By studying these large-scale flows, scientists hope to infer properties of these elusive components and their role in shaping the universe. Supermassive black holes are among the most mysterious and fascinating objects in the universe. Typically, these immense entities are found at the centers of galaxies, where they play a critical role in shaping their host galaxies through gravitational interactions and the emission of energetic radiation. However, a subset of these black holes defies this pattern. These are the supermassive black holes that exist in cosmic isolation, far from any galaxy or observable matter. This phenomenon raises profound questions about the nature of black hole formation and the processes that govern the dynamics of the universe on the largest scales. The existence of isolated supermassive black holes, sometimes referred to as rogue giants, challenges conventional understanding. Normally, supermassive black holes are thought to grow in tandem with their host galaxies. The interplay between a galaxy's central black hole and the surrounding stars, gas, and dust is a cornerstone of modern astrophysics. Yet these rogue black holes are entirely disconnected from visible structures. They drift in the cosmic voids, separated from the dense regions of the universe where galaxies and clusters reside. One possible explanation for these isolated supermassive black holes is their formation during the early stages of the universe. In the aftermath of the Big Bang, the cosmos was filled with vast clouds of gas, which over time condensed to form the first stars and galaxies. Under certain conditions, it is theorized that massive gas clouds could have collapsed directly into black holes without forming stars or galaxies. These direct collapsed black holes could have become the seeds of supermassive black holes in later galaxies. However, if such black holes formed independently and were not gravitationally bound to any galaxy, they may have remained isolated as the universe evolved. Another hypothesis involves the dynamics of galaxy collisions and mergers. Galaxies often interact with one another, merging to form larger structures. In some cases, the gravitational forces during these mergers could eject one of the central black holes from the resulting galaxy. This process, known as gravitational recoil, occurs when the gravitational waves emitted during the merger carry away momentum, leaving the newly formed black hole to be flung out into intergalactic space. If such an event occurred with enough force, the ejected black hole would continue its journey through the cosmos, untethered to any galaxy. Observing these rogue black holes is an enormous challenge. By their very nature, black holes do not emit light, and those in isolation lack the accretion disks of gas and dust that typically make black holes observable through the radiation they emit. Instead, isolated supermassive black holes can only be detected indirectly, often through the gravitational effects they exert on nearby stars or the lensing of light from background sources. Occasionally, a rogue black hole might pass through a dense region of interstellar matter, creating a temporary accretion disk that makes it visible. These fleeting moments offer rare opportunities for astronomers to confirm their existence. The discovery of isolated supermassive black holes also forces astrophysicists to reconsider the relationship between galaxies and their central black holes. The prevailing view holds that black holes and galaxies evolve together, influencing each other through feedback mechanisms, such as the outflows of energy from active galactic nuclei. However, the presence of supermassive black holes in isolation suggests that black hole formation and evolution can, under certain circumstances, occur independently of galaxies. This decoupling challenges existing theories and highlights the need for a more comprehensive understanding of the cosmic processes that govern the universe. Studying these rogue black holes could provide valuable insights into the conditions of the early universe. If they are remnants of primordial black holes, they may preserve clues about the nature of the first structures to form after the Big Bang. They could also serve as laboratories for testing fundamental physics, particularly in understanding how black holes interact with their surroundings, or lack thereof, in the vast emptiness of space. The isolation of these black holes also raises intriguing questions about their eventual fate. In the absence of a galaxy to supply matter for accretion, these black holes may remain quiescent for billions of years, slowly evaporating through Hawking radiation on timescales far longer than the current age of the universe. Alternatively, they could encounter other objects in the cosmic void, such as wandering stars or gas clouds, leading to brief periods of activity. Neutrinos are among the most elusive particles in the universe, capable of passing through vast amounts of matter almost completely undisturbed. These ghostly particles are produced in a variety of high-energy processes, such as nuclear reactions in stars, supernova explosions, and the interactions of cosmic rays with the Earth's atmosphere. Despite their prevalence, detecting neutrinos is a challenge due to their weak interactions with other particles. In recent years, however, a surprising phenomenon has been observed. Regions of space, particularly in galaxy clusters, are inundated by what researchers have termed neutrino blizzards. These are extraordinary concentrations of neutrinos, far exceeding the expected levels based on known cosmic events. Galaxy clusters are the largest gravitationally bound structures in the universe, consisting of hundreds to thousands of galaxies, hot intergalactic gas, and dark matter. These environments are already known to host extreme astrophysical processes, including mergers of galaxies, powerful jets from supermassive black holes, and the acceleration of cosmic rays to incredible energies. However, the detection of neutrino blizzards suggests the presence of additional, unexplained phenomena. The sheer volume of neutrinos observed in some of these clusters cannot be accounted for by standard astrophysical models. This raises fundamental questions about the underlying mechanisms producing these streams of particles. One hypothesis is that these neutrino blizzards may be linked to the decay or annihilation of dark matter. Dark matter constitutes roughly 27% of the universe's mass energy content, yet its nature remains one of the greatest mysteries in astrophysics. If certain dark matter particles are unstable, they might decay into neutrinos and other byproducts over time. Galaxy clusters, being massive repositories of dark matter, could act as focal points for such decays, leading to an excess of neutrinos in their vicinity. Alternatively, interactions between dark matter particles might produce neutrinos in quantities far greater than anticipated. These possibilities, while speculative, align with the observed neutrino fluxes in these regions and may offer a new avenue for probing the properties of dark matter. Another intriguing explanation involves the intergalactic medium, the vast expanses of plasma and gas that fill the space between galaxies within a cluster. In some scenarios, high-energy cosmic rays originating from supermassive black holes or other energetic sources could interact with this medium to produce secondary neutrinos. The resulting neutrino production would depend on the density of the intergalactic gas, the energy of the cosmic rays, and the magnetic fields within the cluster. If conditions are favorable, these interactions could generate the observed neutrino excesses, effectively creating a blizzard of particles spreading across the cluster. The role of supermassive black holes in galaxy clusters is another area of active investigation. These black holes, located at the centers of galaxies, can release immense energy in the form of jets and outflows. When such jets collide with surrounding matter, they can trigger cascades of particle interactions that ultimately result in neutrino production. In some cases, the combined activity of multiple supermassive black holes within a cluster might amplify this effect, producing a sustained neutrino blizzard. This explanation is consistent with the highly dynamic nature of galaxy clusters and their ability to host multiple energetic phenomena simultaneously. It is also possible that neutrino blizzards are a signature of processes not yet observed or understood. For example, the existence of hypothetical particles or forces beyond those described by the standard model of particle physics could lead to novel neutrino-generating interactions. Some theories suggest that exotic particles, such as sterile neutrinos or axions, might play a role in these events. If such particles exist and are abundant in galaxy clusters, their decay or interaction with other matter could produce neutrino fluxes far beyond expectations. The detection of these neutrino blizzards relies on sophisticated neutrino observatories, such as the IceCube Neutrino Observatory in Antarctica. Instruments like IceCube detect the faint flashes of light produced when neutrinos interact with atoms in a large volume of transparent material, such as ice. By analyzing the direction, energy, and frequency of detected neutrinos, researchers can identify their likely sources. The discovery of unexpected neutrino concentrations in galaxy clusters underscores the importance of such observatories in advancing our understanding of the universe. Star clusters are some of the most fascinating structures in the universe, consisting of hundreds or thousands of stars bound together by gravity. Under normal conditions, the gravitational pull in such systems causes the most massive stars to sink toward the center of the cluster over time, a process known as mass segregation. This occurs because gravity naturally pulls the heaviest objects inward, leaving lighter stars distributed toward the outer regions. However, in certain star clusters, scientists have observed an unexpected phenomenon. The most massive stars are found on the outskirts, while less massive stars are concentrated in the center. This counterintuitive arrangement is referred to as an inverted star cluster. The inverted star cluster phenomenon directly challenges our current understanding of stellar dynamics and the physical processes governing star cluster evolution. Gravitational models, which are highly successful in explaining the behavior of most known star clusters, predict the central concentration of massive stars. Yet in these unusual cases, the observed distribution defies these predictions, suggesting that there are unknown forces or processes at work. One explanation for this anomaly lies in the early stages of star cluster formation. Star clusters form out of giant molecular clouds, regions of dense gas and dust in interstellar space. During this formation phase, a complex interplay of turbulence, magnetic fields, and gravitational interactions occurs. It is possible that, in some star-forming ER, another possible explanation involves stellar feedback mechanisms. Massive stars are far more energetic than their smaller counterparts. They emit strong stellar winds, radiation, and in some cases, erupt in violent supernova explosions during their lifetimes. If these effects are concentrated in the central regions of a forming cluster, they could expel surrounding gas and stars outward. This would effectively push the massive stars toward the edges, while simultaneously slowing the inward movement of smaller stars, thus reversing the expected mass distribution. Dark matter is another intriguing factor to consider. Though it remains invisible and undetected by conventional means, dark matter is known to exert a gravitational influence on visible matter. Inverted star clusters may exist in regions with irregular concentrations of dark matter. If dark matter clumps or streams disrupt the gravitational field of a forming cluster, they could alter the dynamics of the system in unexpected ways. Such interactions might not only explain the inverted distribution, but could also provide rare observational evidence of how dark matter interacts with normal matter in star-forming regions. Additionally, external gravitational forces could play a role in this phenomenon. Many star clusters exist within larger galactic environments, where tidal forces exerted by the galaxy's mass distribution can significantly influence the internal dynamics of clusters. If a star cluster forms near a region of strong tidal forces, such as close to a galaxy's core or along the arms of a spiral galaxy, these forces could stretch and distort the cluster, redistributing the stars and potentially causing massive stars to migrate toward the edges. Simulations of star cluster formation and evolution provide further insight into the potential mechanisms behind this inversion. Computer models show that clusters forming in highly chaotic environments with extreme turbulence and rapid gas flows are more likely to develop inverted star distributions. These simulations suggest that the phenomenon may not be entirely rare, but rather an outcome of specific, extreme conditions during the star cluster's birth. Observing more such clusters will help determine whether the inverted distribution is a temporary phase in cluster evolution or a stable configuration that persists over billions of years. The existence of inverted star clusters also raises questions about their long-term stability. In typical clusters, the central concentration of massive stars helps stabilize the system by anchoring it gravitationally. In inverted clusters, the absence of massive stars at the center could make them more susceptible to disruption by external forces, such as encounters with other clusters or tidal stripping caused by their host galaxy. This raises the possibility that inverted clusters may have shorter lifespans than their conventionally distributed counterparts. Cosmic blinking stars, also known as vanishing and reappearing stars, have emerged as one of the most intriguing phenomena in modern astronomy. These stars appear to disappear from observation and then reappear without warning, defying conventional explanations. Astronomers have observed this phenomenon using advanced telescopes, and their findings have raised compelling questions about the behavior of stars and the nature of the universe itself. One explanation proposed for this strange occurrence is the potential obstruction of these stars by massive unseen objects. In some cases, the stars may be temporarily obscured by objects such as rogue planets, interstellar dust clouds, or even massive black holes. Interstellar dust, composed of fine particles of carbon and silicates, is known to block visible light, If such a cloud were dense enough and passed directly between the star and Earth, it could effectively render the star invisible for a time. However, this explanation does not account for all observed instances, particularly when the disappearance happens suddenly or when the reappearance defies expected timelines. Another hypothesis is that these stars are not disappearing in the literal sense, but are undergoing changes that render them undetectable to current observational methods. For instance, stars nearing the end of their life cycle may transition into states that significantly alter their luminosity or spectrum. Certain stars, such as those experiencing extreme variability, can dim and brighten over irregular periods. In some cases, a star could collapse into a black hole without undergoing a visible supernova explosion, effectively vanishing from view. This process, known as a failed supernova, could explain some instances of disappearing stars. Moreover, the concept of exotic stellar behaviors has also been considered. Some theorists suggest that these stars might transition into states that are not yet fully understood or recognized by astrophysics. For example, hypothetical objects such as quark stars or electroweak stars could exhibit properties that challenge our existing models. If a star were to enter such a state, its emission spectrum might fall outside the detectable range of current instruments. These exotic transitions remain speculative, but are being explored through advanced simulations and theoretical physics. Another compelling possibility involves gravitational lensing, a phenomenon predicted by Einstein's theory of general relativity. In gravitational lensing, the light from a distant object is bent around a massive foreground object due to the warping of space-time. In rare cases, this can cause the light of a star to be magnified, split into multiple images, or temporarily obscured. If a star were perfectly aligned with a massive intervening object, its light could be temporarily blocked or redirected, giving the illusion of disappearance. While gravitational lensing is a well-documented phenomenon, the sudden reappearance of some stars suggests that additional factors may be at play. There is also speculation about the role of advanced astrophysical phenomena, including structures or objects beyond our current understanding. For example, some scientists have hypothesized the existence of massive artificial constructs, such as Dyson spheres or megastructures built by advanced civilizations. These hypothetical structures could obstruct a star's light intermittently. While no direct evidence exists to support this idea, it remains a topic of interest in the search for extraterrestrial intelligence, SETI, and has been proposed as one possible explanation for anomalous observations. Another possibility involves highly energetic processes within the star itself. Stars are dynamic systems governed by complex nuclear reactions and magnetic activity. In rare cases, a star's outer layers might eject material in such a way that it temporarily blocks or scatters its own light. This phenomenon could mimic disappearance and reappearance, especially if viewed from a great distance where details of the ejection process are obscured. Additionally, massive flares or coronal mass ejections could create temporary disruptions in the star's light output. A related consideration is the impact of stellar companions in binary or multiple star systems. Many stars exist in pairs or clusters, and their interactions can produce unpredictable changes in light emission. For instance, a companion star could pass in front of the primary star, causing an eclipse-like event that makes the primary star seem to disappear temporarily. In more complex systems, gravitational interactions could alter the star's positions or emission patterns in ways that defy straightforward explanation. In the vastness of the universe, there exist phenomena that challenge our understanding of the cosmos. One such mystery lies in the discovery of immense streams of plasma, known as galactic plasma bridges, that connect galaxy pairs across distances measuring millions of light years. These structures are among the most extraordinary and perplexing features observed in intergalactic space, revealing a new layer of complexity in the relationships between galaxies. Galactic plasma bridges are vast, filament-like structures composed primarily of ionized gas, or plasma, which is the fourth state of matter. Plasma, unlike solid, liquid, or gas, consists of free electrons and ions, making it highly conductive and responsive to magnetic and electric fields. What makes these plasma bridges remarkable is their sheer scale and composition. Spanning distances that can exceed tens of millions of light years, They are far larger than the galaxies they connect, suggesting a scale of cosmic interactions that defies previous expectations. These plasma bridges have been found to be incredibly hot, with temperatures often reaching millions of degrees Celsius. Such extreme heat implies that the energy involved in their creation and maintenance is immense, far greater than what would typically result from ordinary galactic processes. Observations indicate that these structures may be the aftermath of galaxy collisions or close encounters, where gravitational forces and shock waves compress and heat intergalactic gas. During these violent interactions, massive amounts of energy are released, possibly creating these vast plasma connections between the galaxies involved. Another intriguing possibility is that these plasma bridges serve as evidence of large-scale magnetic fields or hidden energy fields that span intergalactic space. Some researchers hypothesize that these fields may be remnants of primordial magnetic fields formed shortly after the Big Bang, or may result from the dynamic interactions of charged particles in the plasma itself. These magnetic fields could play a role in shaping the plasma bridges, stabilizing their structure, and possibly influencing the motion of galaxies over time. One of the most exciting aspects of galactic plasma bridges is their potential role in star formation. Observations have revealed that these structures often contain significant amounts of hydrogen, the primary building block of stars. In regions where the plasma cools and condenses, hydrogen gas could coalesce into dense clouds, triggering the birth of new stars. This suggests that plasma bridges may act as conduits for material exchange between galaxies, fueling star formation and contributing to the growth and evolution of galaxies over cosmic timescales. The discovery of these plasma bridges has been made possible through advanced telescopes and observational techniques, including radio and X-ray astronomy. Instruments like the Chandra X-ray Observatory and radio telescopes, such as those in the Very Large Array, VLA, have been crucial in detecting the faint emissions from these structures. These observations provide critical insights into the physical properties of the plasma, including its temperature, density, and composition. In addition to their physical properties, the distribution and orientation of plasma bridges offer valuable clues about the larger cosmic environment. Many of these structures align with the filaments of the cosmic web, the vast network of matter that forms the large-scale structure of the universe. This alignment suggests that plasma bridges may be influenced by the gravitational forces of dark matter, the unseen mass that makes up a significant portion of the universe's total matter content. Dark matter could play a role in shaping the pathways along which plasma bridges form and evolve. Despite their significance, galactic plasma bridges remain poorly understood, and many questions about their origins and properties persist. For instance, the mechanisms that sustain their extreme temperatures over millions of years are not fully explained. While galaxy collisions and magnetic fields are likely contributors, the precise interplay of forces and processes involved is a subject of ongoing research. Furthermore, the role of dark energy, the mysterious force driving the accelerated expansion of the universe, in influencing these structures is yet to be determined. The study of galactic plasma bridges represents a frontier in astrophysics, with the potential to reshape our understanding of the interactions between galaxies and the nature of intergalactic space. These structures challenge conventional notions of where galaxies begin and end, highlighting the interconnected nature of the universe. By continuing to study these plasma bridges, scientists hope to uncover new insights into the fundamental forces and processes that govern the cosmos. The universe's large-scale structures, galaxies, galaxy clusters, and the vast web of filaments arise from primordial density fluctuations generated during the Big Bang. These fluctuations left faint imprints on the universe's earliest observable light, the cosmic microwave background, CMB. The CMB serves as a map of these ripples, allowing scientists to study the universe's initial conditions. However, while much of the observed universe aligns with these early ripples, a few anomalies deviate from expected patterns, raising profound questions about the forces that shape the cosmos. These anomalies include unexpected alignments and structures that challenge the standard model of cosmology. The axis of evil, for example, refers to a peculiar alignment of the largest temperature fluctuations in the CMB with the ecliptic plane of the solar system. Such alignments defy the expectation that these fluctuations should be isotropic, equally distributed in all directions. This inconsistency hints at unknown forces or mechanisms operating during the universe's infancy. Another striking anomaly lies in the distribution of galaxies on the largest scales. Observations reveal the presence of colossal structures such as the Great Wall and the Sloan Great Wall, vast aggregations of galaxies spanning hundreds of millions of light-years. These structures seem to align with patterns in the CMB, but also exhibit deviations that challenge conventional theories of structure formation. According to the Lambda Cold Dark Matter (LCDM) model, such structures should have formed gradually under the influence of gravity acting on initial density ripples. Yet their size and coherence suggest the possibility of additional influences, potentially arising from exotic physics. One hypothesis involves unknown types of particles or forces that could have altered the density fluctuations in the early universe. During the inflationary period, when the universe expanded exponentially within a fraction of a second after the Big Bang, quantum fluctuations were stretched to macroscopic scales, imprinting the seeds of large-scale structure. However, if inflation involved interactions with particles or fields not accounted for in current models, this could explain the observed deviations. For instance, some theories propose the existence of primordial magnetic fields or other exotic phenomena that could have influenced the inflationary process. Another possibility is that certain anomalies arise from interactions between dark matter and other components of the universe. Dark matter, though invisible, is known to exert gravitational influence and shape cosmic structures. If dark matter particles interact weakly with ordinary matter or radiation, they could have left subtle but measurable effects on the early universe. Such interactions might distort the patterns of ripples in the CMB, resulting in the anomalies observed today. The role of dark energy, which drives the accelerated expansion of the universe, also cannot be ruled out. While its influence on structure formation is minimal during the early universe, it might play a subtle role in how large-scale patterns evolve over cosmic time. Alternatively, the anomalies could point to a breakdown of our understanding of gravity itself. Modified gravity theories, such as those proposing variations to Einstein's general relativity, might explain discrepancies in the distribution of matter and energy. Compounding these mysteries, some anomalies may reflect limitations in observational techniques or data analysis. The CMB is a faint signal, and separating it from foreground emissions, such as those from the Milky Way or intergalactic dust, is a challenging task. It remains possible that some deviations are artifacts rather than true features of the universe. Despite these uncertainties, the study of these anomalies is far from speculative. Scientists continue to probe these questions with increasingly sophisticated tools. Observatories like the Planck satellite have provided high-resolution maps of the CMB, enabling detailed comparisons between theoretical predictions and observed data. Future missions, such as those involving the James Webb Space Telescope and next-generation CMB experiments, aim to further refine our understanding of the early universe and its ripple patterns. The unexplained deviations in the universe's large-scale structure are not merely curiosities, but potential windows into the physics of the Big Bang itself. If confirmed, they could redefine our understanding of cosmology, shedding light on the nature of inflation, the composition of dark matter, or the influence of unknown forces. Each anomaly carries the potential to expand the boundaries of human knowledge, offering clues to the fundamental processes that shape the cosmos in its earliest moments.